We will discuss how to apply u-substitution to evaluate definite integrals, which involves some basic properties of definite integrals, as well as the fundamental theorem of calculus. The properties on this screen can be used to facilitate calculations. The first property states that if the function f is an odd function and the limits of integration are symmetric, then its definite integral is 0, as shown on the first line. The second property states that if the function f is an even function and the limits of integration are symmetric, its definite integral is displayed on the second line. The third property states that if we swap the upper and lower limits, a negative sign is introduced, as shown on the third line. The properties on this screen can be used to facilitate proving certain properties of the Riemann integrals. The first property states that if we know the values of the function f on the closed interval a to b are bounded between lowercase m and uppercase m, then we also know that its definite integral is bounded between lowercase m times b minus a and uppercase m times b minus a. The second property states that the absolute value of the definite integral of a function is less than or equal to the definite integral of the absolute value of the function. This example involves computing the definite integral on the second line. The substitution for variable u is set on the third line. When applying substitution to a definite integral, the limits of integration also change. Originally, the lower and upper limits of integration with respect to x are 0 and 1/2, respectively. When x equals the lower limit 0, substituting it into the expression for u yields the lower limit u equals 1. When x equals the upper limit 1/2, substituting it into the expression for u yields the upper limit u equals 0. The complete computation process is displayed on the last two lines. On the second to last line, the first equal sign represents the definite integral after substitution. Note that the limits of integration must be changed accordingly. The second equal sign uses the property that swapping the upper and lower limits introduces a negative sign. Typically, we require the lower limit to be smaller than the upper limit. Finally, the last line simply evaluates the antiderivative at the upper and lower limits, subtracting the value at the lower limit from the value at the upper limit. This example involves computing the definite integral on the second line. The substitution for variable u is set on the third line. Originally, the lower and upper limits of integration with respect to x are 0 and square root of 3, respectively. When x equals the lower limit 0, substituting it into the expression for u yields the lower limit u equals 1. When x equals the upper limit square root of 3, substituting it into the expression for u yields the upper limit u equals 4. The complete computation process is displayed on this page. The first line represents the definite integral after substitution. Note that the limits of integration must be changed accordingly. The second line is simply algebraic simplification. The third line evaluates the antiderivative at the upper and lower limits, finally yielding the integral value on the last line. This example involves computing differentiation after integration, as shown on the second line. The last line illustrates that after evaluating the integral, we obtain sine of x cubed minus sine of 0, which is then differentiated to complete the calculation. Problems of this type, which involve differentiating an integral, take the form of the fundamental theorem of calculus. If the function f is continuous and the function u is differentiable, then the formula for differentiating an integral is displayed on the second to last line. Here, the lower limit of integration is a constant, while the upper limit u is a differentiable function of the variable x. Note that we are differentiating with respect to the variable x in the upper limit, not with respect to the dummy variable t in the integrand f. From this theorem, we can see that it is not necessary to actually evaluate the integral before taking the derivative. The working formula is shown on the second to last line. In fact, even when some functions do not have an elementary antiderivative, we can still perform the calculation, as shown in the next example. This example involves computing differentiation after integration, as shown on the second line. We notice that this function has no elementary antiderivative, yet we can still calculate the derivative of the integral by applying the formula from the previous page. The calculation process is displayed on the last line. This example involves computing differentiation after integration, as shown on the second line. As before, it is not necessary to actually evaluate the integral. We simply apply the formula from the Fundamental Theorem of Calculus. The calculation process is displayed on the last line. This example also involves computing differentiation after integration, as shown on the second line. However, the lower limit of integration is now the variable x rather than a constant a. Therefore, we need to split the integral into two terms. The fourth line applies the additive property of definite integrals, breaking the integral from 0 to 2x into the integral from 0 to x plus the integral from x to 2x. After algebraic manipulation, we obtain the mathematical expression on the last line. In other words, we decompose the integral whose lower and upper limits were both functions of x into integrals that both have a constant lower limit. The purpose of this step is to enable the use of the formula from the Fundamental Theorem of Calculus. Next, differentiating both sides with respect to the variable x yields the equality on the second line. Finally, applying the formula from the Fundamental Theorem of Calculus completes the calculation, as displayed on the last line.